So here we have a circuit, and it's got several loops in it. We've got resistors here, like this 10 ohm resistor, this 5 ohm resistor. The voltage drop across a resistor is V equals IR, Ohm's law. And so I'm going to write that by Q prime. So ohms would be in coulombs, or sorry, amperage would be coulombs per second. So it's a rate of change of the Q, the charge. So Q prime times the resistance. An inductor, here's a 20 Henry inductor here. The voltage drop across an inductor is proportional to Q prime prime, so LQ prime prime, and across a capacitor here, 1 over C times Q. So this will be very quick as far as jumping in and, Kirchhoff's laws and that. We're just going to try and get to the equations as quickly as possible. And the point of this video is to show solving those equations with Laplace. So let's take a look at our equations then. Okay, first thing is we've got the current goes through the battery and then it splits. I2 goes through this this inductor, and then I3 circles around and goes through this 5 ohm resistor and this capacitor, and then they join. So I1 equals I2 plus I3, that's Kirchhoff's current law. And since I is Q prime, we got Q1 prime equals Q2. So this is our first equation with the Q's. Where I'm going with this is there's going to be 3 Q's, and I want differential equations with all the Q's in them. So there's the first differential equation with the Q's in them, Q1 prime, Q2 prime, Q3 prime. So we're going to end up with a system of differential equations. There's 3 dependent variables, the Q1, Q2, Q3, and time is the one independent variable. Now I'm going to look at this left loop here. This left loop, it's 10 volts in, then there's a voltage drop across this resistor, and then a voltage drop across this inductor. So the left loop is giving me this equation. 10 in is equal to V equals IR, the resistor, and here's our inductor. The big loop, 10 in, drops on the resistor, drops on the resistor, drops on the capacitor, and then loops around. Now it's I1 that's going through the first 10 ohm resistor, but it's I3 that goes through this 5 ohm resistor and this capacitor. Again, you might need to pause the video and check this out. This is just, I'm trying to get to the equations as quickly as possible. So here's our big loop equation. So our Kirchhoff's current law, I guess I'm using Kirchhoff's voltage law to get these left loop and big loop equations. Here's my 3 equations, 3 differential equations that have the Q1, Q2, and Q3 in them. So now I'm going to Laplace everything, take the transform. So when I take the transform of this left loop equation, all of this Q1 prime changes into SQ. So the Laplace of Q1, little q1 is big Q1. So here's my Laplace of Q1 prime, my Laplace of Q2 prime prime, and all these sub knots, this would represent the Q2 knot, and so on. So those are all constants that would have to be given in the question. But notice, once I Laplace this left loop equation, there's no more derivatives. So I've only got Q1 and Q2 in this equation. When I take the Laplace of this Kirchhoff's current law, replacing taking the Laplace of the Q1 prime, etc., I end up with only Q1s, Q2s, and Q3s, a linear combination of the Q1s, Q2s, and Q3s. Taking the Laplace of the big loop equation gives me, the Laplace of 10, the Laplace of Q1 prime. Again, I'm just following your standard Laplace transforms of this. I end up with 3 equations. This is 1 equation, this is 2 equations, this is three equations, and there are three equations, three unknowns, and those unknowns are three linear equations in three unknowns, and those unknowns are capital Q1, Q2, Q3. So I'm gonna take the equations and do like this sort of thing, right? Make it a linear combination of the Q's is equal to a constant. Remember all the knots, the Q1 knot, the Q2 knot, the Q3 knot, those are all constants that will be given. So three equations, three unknowns, I just need to solve for Q1, Q2, and Q3. Capital Q1, capital Q2, capital Q3. What I'm going to do is I'm going to write them out in matrix form. Now you don't have to do this. This is just the easiest way for me to do it anyway. So I've written this out in matrix form, those three equations, and now I can take the inverse of this matrix, multiply it by this constant vector, and solve for Q1, Q2, and Q3. So, or you could solve by substitution or however you want. Here's the inverse of that matrix multiplied by the constants, and then I end up getting, when I do that, I end up getting, oh, well, okay, before we do that, this is the inverse of the matrix times the constant vector. When I do that multiplication, I'm going to end up getting I'm going to end up getting the vector with the Q's is equal to that. At this point, just to make the explanation easy, let's actually put in numbers for the Q1 knot, Q2 knot, and Q3 knot, as if they were given in the question. Let's pick something simple, like I'm going to make them all 0. So the initial conditions are all 0. When I do that, I end up getting, well, that's going to make all of this piece 0 when I make all the Q's 0, the knots. I end up getting this matrix then times with all the zeros, and when I multiply it out, this is what I get. So this is equal to Q1, Q2, Q3. That means that I can write Q3 is equal to, so that's in the Laplace world, is equal to, when I do partial fractions, so if I do partial fractions on this and break it up, that's what I get. Now I can unLaplace. That means Q3 must be equal to, taking the inverse Laplace, 4/5 e to the minus 2/3 t minus 4/5 e to the minus 3/2 t. And there's my Q3 function. I could likewise solve for, I've got Q2 equals, I've got Q3 equals. We could do partial fractions on each piece. But this Laplace way then, oh, okay, so this, without Laplace, this would have taken us much longer. And it's much more difficult because you have to be clever on how you substitute one equation into the other, and you try and get at the end, a linear second order constant coefficient differential equation, all in terms of like some number Q1 prime prime plus some number Q1 prime plus some number Q1. In other words, all the Q's are 1s or 2s or 3s, and then you solve it in the standard form. But with Laplace, it gets rid of all the derivatives. You end up with a system of three unknowns, three equations. The three unknowns are the Laplace of Q1, capital Q1, the Laplace of Q2, that's capital Q2, etc. And then you can just systematically solve for one of the Q's, the uppercase Q's, the capital Q's, and then you just unLaplace to solve it.